Dear colleagues and friends, I would like to start by expressing my gratitude to the organizing committee of ISC6 and to board members of TC 102 on in situ testing for the invitation to deliver the 9th James Mitchell Lecture on the geomechanics and geocharacterization of tailings. I'll start by recalling that some important advances in the interpretation of in situ testing have been reported in previous lectures. So the objective of this presentation is to add new information, to cover some recent research issues on the subject, and highlight trends that emerged from recent accidents in tailings storage facilities. The outline of the presentation is fairly simple. I'll sort of set the grounds by discussing some experience gathered from the failures of tailing dams before moving to other technical issues, covering the background theory for the interpretation of in situ tests, concentrating on rate effects, which is a requirement for the prediction of constitutive parameters. I'll make then some brief comments on how to predict the coefficient of consolidation, state parameter, shear stiffness, and shear strength before heading to conclusions. As an introduction, I'll sort of try to give a general perspective of the topic, always from the geotechnical point of view. And I'll start by sharing some of my personal experience that involved studying the two major recent accidents in Brazil, the Fundão and the Brumadinho Dam. I'll sort of try to briefly highlight the lessons learned from these accidents and how they're guiding our research efforts in Brazil, which is somehow reflected in this presentation. The Fundão Dam is an upstream construction that failed in November 2015, releasing over 45 million cubic meters of mine tailings and killing 19 people. An investigation was performed to determine the causes of the accident by a review panel that was led by Professor Morgenstern. We all know about that. Field evidence have been gathered, advanced lab testing performed, and the work was supported by sophisticated computer modeling. I should remember that the structure was well maintained, monitored, and documented, although the review panel acknowledged that that structure was vulnerable by a series of unplanned occurrences. From the geotechnical point of view, which is the point that brings us here, the profile was stratified with highly interbedded materials comprising sand tailings and slime layers of clay-like behavior. The tailings were loose, saturated, and susceptible to liquefaction. The failure mechanism of the structure was attributed to this soft, low permeability slimes layer that were compressed and eventually squeezed out by lateral extrusion. And let's accept that this trigger mechanism is not an easy one to be considered or to be anticipated. This is a general view of the area 2 weeks after the accident, and at the background you can see the Germano Dam, which is a twin dam that is operating in the same location. As for the Brumadinho Dam, there are some similarities, but it's worth mentioning that there are no risings after 2013 and tailings disposal ceased in July 16. So the Brumadinho Dam was discommissioned for more than 2 years and a half before the accident that killed 270 people. This is some views of the Brumadinho Dam. These images taken just before the accident, and this one just after the accident, 6 minutes after the accident, in which you can see the amphitheater here and what was left from the impoundments. Insights as to the reasons of this 2019 accident were summarized by in a causation report that was led by Professor Peter Robertson. The material was described as having a brittle response, which was attributed to iron oxidation. The strength, this failure was triggered by a critical combination of ongoing internal strains due to creep and combined to the loss of suction in the unsaturated zone that was caused by intense rainfall towards the end of 2018. So again, let's accept that identifying creep strains taking place inside a reservoir is not an easy problem to be approached in terms of design and in terms of evaluating risk. Interesting enough, another independent report was issued by the Brazilian Federal Police that was working in combination with an international research group, and they reached a different conclusion, attributing failure to ongoing drillings for in situ testing and for installation of instruments. So what are the lessons that one can take from these two accidents? In both cases, we're talking about our tailings that were hydraulic deposited, were non-plastic materials, and were known of exhibiting high potential to liquefaction. There were no warnings in both cases. These failures have not been anticipated by the instrumentation. And in both cases, trigger was not easily identified. And I was talking about the ongoing debate on the Brumadinho failure. Although the mechanism itself was not easily perceived, we know that it is geotechnical. So it's up to the geotechnical community to react and improve our ways of estimating the strength, the stress, strain, and strength behavior of these materials, and to identify their contractive response. And that's exactly the aim of the present presentation. I'll then move to more technical issues, as I mentioned before, and I'll start by critical state soil mechanics. And of course, there is no intention to review the theory, but just to highlight some aspects of behavior. The mechanism of soil liquefaction, or else the stress-strain behavior of this material can be described by critical state soil mechanics without requiring no new soil properties or concepts to be added. And I'll highlight this behavior, I'll illustrate this behavior by the results of triaxial compression and extension tests performed in gold tailings. From these tests, we could derive the critical stated line, and there are some important aspects to be discussed. The first one is that the tested tailings show a unique critical state line, which is one of the axioms of critical state theory. But there is a characteristic feature of these tailings, and that is the fact that the critical state line exhibits a marked curvature that is dictated by transitions of state, going to full liquefaction, to flow instability, to a stable zone, and eventually to particle breakage at very high stresses. The slope of the critical state line, as you can see here, becomes fairly flat at low mean stresses, with the drain shear strength reducing continuously due to the strong strain-soft response of the samples, of the tested samples. As the mean stresses increase, the behavior gradually evolves to strain hardening. An additional feature that I think is important to mention is the requirement for measuring the shear stiffness by bender elements, because strength and stiffness are coupled, and by coupling these two quantities, we improve our ability to derive soil properties from the interpretation of in situ tests. Another point which is worth highlighting is that this behavior is not unique to gold tailings. Critical state lines of different tailings, as shown in this plot from a work by Lee, Coop, and myself, clearly identify that most tailings show this curved critical state line that is fairly flat at low to medium stresses, but tending to be parallel to the corresponding normal consolidation lines at high stresses. I suppose that nowadays there are more than 20 to 30 constitutive models that have been developed for sands, some of which have already incorporated the nonlinear equations to express the shape of the critical state line. So what is the question mark? We aim at determining the constitutive parameters in tailings, and we do so by combining in situ and lab tests, having the critical state soil mechanics as the background theory. When talking about lab tests, we can use undisturbed or reconstituted samples, but with the difficulty of retrieving undisturbed samples in silty sands, one usually resorts to reconstituted samples. We are now in a position of moving to in situ tests, and we are going to concentrate, as I mentioned previously, on rate effects, because in these intermediate permeability materials, the standardized testing rate may lead to partial drainage, and thus to erroneous estimation of undrained parameters. We do that by expressing results of different in situ tests as a function of a function of the normalized velocity of the normalized velocity. The normal velocity is a kind of classical concept that comes from pore fluid pressure diffusion in linear pore elastic mediums. There are several expressions that have been proposed on the basis of this concept, and they all capture the key elements which needed to be considered for in situ testing interpretation. And here you find one example that relates the normalized cone resistance in respect to the normalized velocity. And you see this plot, as a matter of fact, it combines centrifuge, calibration chamber, and field tests. And a simple observation of the reported data shows that the influence of partial drainage on cone resistance is significant in all materials. If you see the red line, which are gold tailings, this is the normalized cone resistance that represents the drained value in respect to the undrained value that's taken at much higher normalized velocity. So I think that you're kind of familiar with this concept, and the idea here is how to approach this problem in engineering practice. And there are essentially two alternatives to be considered. The first alternative is just emerging from the previous explanation. Non-standard penetration rates or testing rates may have to be selected according to local experience in order to ensure that either fully drained or fully undrained shear conditions are achieved. But there is another alternative, which I think is one that is required and has not been extensively discussed by the geotechnical community. There is a large database, a comprehensive database of in situ tests carried out according to international reference test procedure. And I think the question is whether we are able to correct these in situ measurements to account for the possible errors induced by pore pressure dissipation. And this later approach will be discussed herein. So I'll show this looking at different in situ tests, and I'll start by piezocon tests, by the interpretation of piezocon tests. I'll start by quantifying the maximum error in calculating the shear strength, which is given by calculating the normalized drain to undrained cone resistance, which is here plotted against the internal friction angle. The predictions are based on a fairly simple rigid plastic model that has been calibrated against recent published data, including tailings. And as you can see, this model prediction yields a ratio of drain to partial drained cone resistance of the order of 10 or as high as 10. And this ratio can be approximated by an exponential function. So when trying to make corrections, one has to be careful. It needs engineering judgment because this correction can be quite high. But besides, it's possible to provide guidelines for design by directly correcting the tip cone resistance recorded at the standard penetration rate of 20 millimeters per second in order to calculate an equivalent fully undrained penetration resistance. And this is done also by a fairly simple expression that is a function of the internal friction angle and BQ. So the proposed expression is can be seen or should be seen as a first approximation supported by experimental data that stands until more rigorous solutions are derived. So this was the first example. The second example is related to the vein test, to field vein tests. And I suppose that this is a fairly important and interesting interesting test to be discussed because it is a reference reference test for clays. But the standard rate of vein rotation of 0.1 degrees per second that ensures undrained conditions when shearing clays may not be applicable to estimate these values in silts, in transitional soils. So we've got to evaluate what is the possible error that is inherent to this type of tests in silty tailings. This is one example. You see some results where the torque is being measured at different rotation rates. But when one tries to evaluate the drain curves from the measured torque expressed as a function of the normalized velocity, there is an experimental problem. For being able to go from undrained to drain torques, we would have to increase the rotation rates by 1,000 times, which we are still unable. So the alternative is not relying just on measured data on experimental data, but we have to extrapolate the curve to get an entire description of the drain conditions taking place on a rotation vane. And this has been done in this particular example, considering a poromechanical analysis of consolidation induced by the rotation not of a vane, but the rotation of an infinite long rigid cylinder embedded in a porous medium. And the results are quite interesting. The study demonstrates that the ratio between the drained and the undrained torque is governed by the internal friction angle. The model predictions are generally lower than 2.5, some of this order, which is much lower than the values calculated for the piezo cone. And this can be explained by the fact that the volumetric strains induced by vane rotation in a drain regime are moderate in comparison to values calculated by cavity expansion, which is related to the piezo cone. So corrections are relatively small, and we may be tempted to use this type of approach for correcting the vane tests. Incidentally, the ratio is described by a hyperbolic function expressed, of course, as a function of the friction angle. If you want now to extend this approach to formulate an approximate expression to correlate the measured torque or the torque measured at a standard vane velocity in comparison to its counterpart under undrained conditions, it is also possible, and is expressed by a very simple equation that's a function of the internal friction angle and the normalized velocity. So this is a ready-to-use equation if one tries to derive soil parameters from vane tests in silty soils. I'll now move to something that's slightly different, because with the dilatometer, it's not possible to make a correction of the test data. But what we have to do is an adaptation of test procedures. To be fair, since the early days, Silvano Marchetti has acknowledged that in transitional soils, the after installation DMT readings are changing continuously with time due to excess pore pressure dissipation. So we are using this decay curve for what is being called as an integrated approach. After completion of the pore pressure dissipation at the minimum lift-off pressure, the membrane can be inflated, and these values can be used to derive or to estimate the internal friction angle. Alternatively, we can extrapolate this curve back to the origin to get an equivalent undrained lift-off pressure, and this can be used to predict the undrained shear strength. Of course, that as for the CPT, if the penetration process of the DMT is partially drained, the extrapolation to determine this value will be incorrect. There is a new device, and I would like to call your attention to that, the Medusa DMT, that is able to monitoring the variation of array A readings with time, and that enhances our ability to use the DMT for interpretation of testing data in silts. I'll finally move to the standard penetration test, which is a slightly more complicated issue, more controversial issue, but I'd like to make some comments on that. When you talk about dynamic penetrometers, we know that the results exhibit poor repeatability. There is lack of standardization of test procedures and unknown values of energy delivered to the SPT rods, as well as the variable penetration rates taking place during a single blow, which are limiting factors that may result in misleading predictions when using this information. As a means of assessing liquefaction, the SPT fulfills the need for retrieving undisturbed soil samples to determine the water content, fines content, and Attenberg limits. But in granular soils, there is another alternative which I like to highlight for you in this presentation. For tests carried out under drain conditions, we developed a rigorous solution to circumvent some of the inherent limitations associated to SPT interpretation by calculating a dynamic force. And this force is simply calculated using the principles of energy conservation and wave propagation analysis with no empirical or adjustment factors. So when using this dynamic force, we can calculate an equivalent dynamic penetration, and we can compare the results of the SPT with the results from the CPT, which are here shown in green for several logs that have been carried out on a dike. And you see that in this particular example, there is a consistency between SPT and CPT records when that allow a direct comparison between all these tests. So we do analysis and we do account for rate effects, we are then able to derive constitutive parameters in tailings. Of course, you understand that there are two major principles for that. The first one, rate effects have to be considered either by correcting the measured data or by making adaptations in test procedures. And we have been discussing that previously throughout this presentation. The second is that there is a need to combine field and lab tests. So let's give some examples. Some of them I will sort of discuss briefly, and some of them I will sort of concentrate and discuss on a slightly more detailed way. We can look about stiffness. If you talk about soil stiffness, it is well recognized that the geotechnical site characterization can be improved by independent seismic measurements, adding the downhole shear wave velocity to the other in situ testing data. As a matter of fact, the small strain stiffness G0 is among the most reliable and easy constitutive parameter to be measured, both in the field and in the laboratory. Conversely, if you look about the coefficient of consolidation, this is rather more complicated because partial drainage effects during piezocone penetration may violate the boundary conditions assumed in the interpretation of piezocone dissipation tests, either when one-dimensional cavity expansion or two-dimensional strain path methods from which both monotonic and dilatory soil response can be modeled. And this is not to mention the uncertainties in determining the phreatic surface location in tailing dams. So you see that the approach of each of these parameters have to be properly evaluated from some physical assessment of what is involved in the interpretation. If we move to drained properties, we can look at the state parameter or the internal friction angle. And I recall that here we rely less on theory and more on experience gathered from calibration chamber tests, recalling that most of the tests were carried out on clean, unaged, uncemented sands. There are, as a matter, the current engineering practice when trying to derive the state parameter relies heavily on correlations established from CPT measurements. As you can see here from the work of Jeffers, Bean, and co-authors, or Peter Robertson. But there are other alternatives, such as the seismic cone, in which the state parameter is assessed from a combination of G naught upon QT, a small to a large strain ratio, which enhances our ability of deriving the state parameter. We can also rely on the cone pressure meter or on the dilatometer. These are ready-to-use equations that are generally used in engineering practice. But I'll try to illustrate the state parameter variation derived from seismic CPT tests carried out on a beach very close to the upstream face of a tailings dam, towards the right and the left abutment, respectively. And as you can see here, it's interesting because the two CPT-based methods yielded fairly similar trends. But by adding the contribution of soil stiffness, the SCPT-based state parameter variation agrees sufficiently well with the CPT values in the right abutment, but indicate a predominancy of dilative tailings in the left abutment. So why am I bringing this example? Is to draw your attention to the fact that none of these methods give a correct estimation of the state parameter in non-plastic sealed tailings. They should be seen as an approximation because the influence of fines is not completely understood, and cavity expansion methods used to calibrate these approaches were essentially based on clean sand. So this type of approach should be viewed as the first step guiding the need for further investigation. I'll make some comments on the internal friction angle, but I think they're fairly similar. Correlations with the cone tests are widely used in engineering practice to derive the internal friction angles, but alternative methods include the seismic cone, the cone pressure meter, the dilatometer, and even the SPT. But recall what I was saying for the state parameter. For the same reasons, these correlations should be viewed as a first approximation in silts or in silt tailings. So as a general recommendation is to apply these correlations in silts, having the critical state friction angle as a reference value. In other words, always carry out some triaxial compression tests to determine the critical state friction angle, and then compare your correlations in respect to the property of to this property that's easily determined from different materials. As a guideline for design, we try to establish a correlation between the critical state angle and the mean particle size for different non-plastic CUT tailings. As you can see here, most internal friction angles for different silted tailings, they fall within this narrow range of about 31 to 35 degrees, despite the variability in mineralogy and particle shape expected for this material. And this scatter seems to be much lower than the one observed for sands. We can now move to the final part of this presentation just to make some comments about our ability in predicting the undrained shear strength. We know that the undrained shear strength in tailings, common in all soils, depends on the mode of failure, the rate of shearing, soil anisotropy, and stress history. Therefore, it is not a unique soil parameter, being strongly dependent upon the method by which it is determined. So this is a problem, but on the other hand, we can rely on the concepts of critical state soil mechanics just as long as rate effects are properly being taken into account. However, there is again one complicated issue. In discussing the shear strength of liquefied soils, it is necessary to distinguish among the different measures of strength in saturated, strained, softening soils. We can be talking about the critical state strength or the residual shear strength or even the liquefied shear strength, which incidentally is not replicated in lab element tests. So let's see how we approach this value. If we are talking about the peak and drain shear strength, we are in familiar grounds. So I don't have to extend on that because we know we can rely on the piezo cone, on the full flow penetrometers, the vein tests, or the dilatometer to derive these quantities using well-known equations. However, estimating the residual post-liquefaction undrained shear strength is another matter if we're talking about materials that are susceptible to liquefaction. Essentially, that's not even a geotechnical problem. It is more related to soil rheology because the material behaves as a non-Newtonian fluid. So current engineering practice, current engineering design practice tries to overcome the uncertainty in assessing SU from relationships established directly from field performance experience. And there are all sorts of uncertainties associated to this type of approach. I even recall that new guidelines require the strength reduction to be applied to all materials independently whether the factor of safety against liquefaction is greater or less than 1. So if this parameter becomes a key parameter in design, it's got to be measured, and we've got to improve our ability in try to estimate this value. One alternative which I like to call your attention to, which is related to current research that has been carried out in Brazil, is related to the full flow penetrometers. I'm talking about the piezo ball or the T-bar. And you see here a set of interesting results in which the undrained shear strength or the variation of undrained shear strength with depth has been evaluated in this particular location, but this probe has been halted at given depth to perform unload reload in cycles from which the drain shear strength reduction could be evaluated. What is interesting about these results is the fact that these tools are research tools in which the pore pressure is being measured in 3 different locations. One in the hemisphere, one in the pole, and another one in the meridian, if you like. So the idea is trying to look at the pore pressure generation and dissipation to see if we can identify the mechanisms that are associated to strength reduction in different geomaterials. So these were some of the aspects that I would like to discuss, and I think that conclusions have been drawn throughout this presentation. We understand that the challenge for us is to derive constitutive parameters. This is the core of the various geotechnical analysis required through the lifetime project of geotechnical structures. The geotechnical community is reacting to the challenge that have emerged from these accidents, but we understand that further research is needed. And I'll leave you with two questions. If slope stability of tailing storage facilities should be addressed by using limit equilibrium analysis, I think that we've got to enhance our ability to develop appropriate procedures to evaluate the residual post-liquefaction and drain shear strength. And this is one aspect that has been highlighted throughout this presentation. If, on the other hand, advanced constitutive models are to be adopted, we've got to develop means of assessing the related constitutive parameters. So we have said that, I complete this presentation, and thank you very much for your attention.